Today we'll be working on the following problem. Suppose V is an open in Rk, the k-dimensional Euclidean space, and mu is a finite positive Borel measure on Rk. So we want to ask the question, is the function that sends x to the measure of V plus x necessarily continuous, lower semi-continuous, or upper semi-continuous? So pause the video if you want to work on this problem by yourself. Okay, let's work on our solution. We first claim f, okay, by definition we have this f of x send x to mu of v plus x. V plus x is just v translated by x, right, in this vector space Rk. And then x is in Rk. Okay, first f is not necessarily continuous, or even upper semi-continuous. So we prove this by given example. For example, let's define for any set in R of k, we can define the measure of this E to be, if the origin in E, the measure is 1. If the origin is not in E, we define to be 0. And then, it's easy to verify mu is a positive finite Borel measure. It's easy to verify. And now we let V to be the unit ball, the open unit ball, which is x in Rk, and then the norm, or we use absolute value. The norm is just the norm in the Euclidean space, right? K-dimensional Euclidean space. The norm is less than 1, so this is just the unit ball. Now let's find, so f of x is, under our condition, definition, is v plus x, which is 1 if 0 is in v plus x. And then if 0 is not in v plus x, the value is 0, right? And this is equivalent to say, because v is the unit ball, this is just if x in v, and this is if x is not in v, right? And then so it is the characteristic function of v, f of x. So this is not a continuous function, and then it's just a step function, right? So, and also it's not upper continuous because, for example, f of x less than 1/2 for all the x, this set is what? It's just the complement of v, right? So Rk minus v is, this is not open. Actually, it is closed, not open. So f is not continuous, right? Not upper semi-continuous. So this is just example, right? So this proof like f is not necessarily continuous, not necessarily upper continuous either. So now we want to show like f is actually lower semi-continuous. For any v and x, right? So let's first, two trivial cases. If v equal to empty set, this f of x is just the measure of empty set, which is 0, right? So if v is the entire space, f of x is, is just translate by x is the whole space itself, which is a constant. And then both case, their constant is lower semi-continuous, right? So we can assume like so let's work on the v is not empty and is not the entire space. So for any alpha in R1, we want to show this set, x in Rk, and then f of x greater than alpha. We want to show this set is open. Once we show this set open for any alpha, then f is lower semi-continuous by definition, right? So from here, let's without loss of generality, like we can assume G is non-empty. So we pick x sub 0 in G. So then we have f x sub 0 is greater than alpha, and this is the same as mu of v plus x sub 0 is greater than alpha. So now here we want to use because mu is a positive Borel measure in this Euclidean space. We know mu is actually regular. So when mu is regular, we can say like this the measure is just the supremum of all the measure of a compact subset of v plus x. So this is compact, and then f is a subset of v plus x sub 0, right? So that's a supremum. So the supremum is greater than alpha. Then we can find a f, compact. F is a subset v plus x sub 0. And then the measure of f is greater than alpha. So now our task is like, how do we show, G is open? So we have a point x sub 0 in G. So basically x sub 0 here. We want to find some neighborhood with the, the radius delta such that f of x, for any x in this neighborhood, f of x is also greater than alpha, right? So so from here, because f is compact, so if we translate by minus 0, this also a subset of v, f minus x sub 0 is compact set, and then shifted by a fixed x sub 0 is compact, right? And then because this is a subset of v, with rk minus v, this set, and f minus f sub 0, this set, these two sets are disjoint, right? So, but this is closed. It's closed set. And this is compact. And then they are disjoint in RK. So from the problem we have worked on before, or you can also derive it directly. So we know there exists delta greater than 0. So basically you have these two sets, f minus x0, and then another closed set. So there is some distance, right? The distance is greater than 0. So which means like we have for all, if y is in this RK minus V, the complement of V, because we assume V is not the entire space, not empty, so there is some Y, right? And then for any Z in F minus X0, so Z is here, and then Y is here, the distance, Y minus Z, the norm, is greater or equal than delta, right? So we find some delta which has this property. Now we are going to use this to prove, this G is open. So to do that, let's use this delta. Like now for all x, if x minus x sub 0 is within delta, we claim that when f is shifted by this x, is a subset of V. So once we have this, what do we have? Then we have f is in V plus x, right? So a f of x is the measure of V plus x, because f is a subset of this. This is greater or equal than the measure of f. But we already know the measure of f is greater than 0, so greater than alpha. So this greater than alpha. What do we have? So we, from x sub 0, we find a delta neighborhood. If for any x in this neighborhood, we have f of x greater than alpha, which means, gives the conclusion, which gives that a G is open, right? So when G is open, by definition, F is a lower semi-continuous. So all we want to know is, so from here, so we want to basically prove this. So if this is not a subset of V, this means there exists y sub 0 in this f minus x, and y sub 0 is also in the complement of V, right? In the complement of V. But then this means like y sub 0, we can write this y sub 0 is some f sub 0 minus x. F sub 0 is in F, right? So now when we look at since F sub 0 is in F, so let's do this. F sub 0 minus x sub 0 is in F minus x sub 0, right? Because F in this. So what do we have? We have y is in this set. And then f sub 0 minus x sub 0 is in f minus x sub 0, right? So if we subtract this, or we shift this, so we have f sub 0 minus x, and then minus this f0 minus this. So by definition, we know this y sub 0 is in the complement of v, and then f sub 0 minus x sub f sub 0 minus x sub 0 is in this set. So we already know, like, from here, for any y in this z in here, this has to be greater or equal than delta by, let's see, this, right? However, but this is just x minus x sub 0. But this contradiction, right? Because we pick x to be within the neighborhood of x sub 0, within delta. This is what x is. And now we have also this contradicts to this the choice of x, right? Contradicts to x minus x sub 0 is less than delta, right? So meaning like this is impossible, which meaning like f minus x has to be a subset of v. And then we're going back, this means like G is open. So we're done.